Before I introduce the speaker, I've tried to give a little context behind what this is all about and how all this came to this point. So as you know, there is a study abroad program called the European Study Center Program for engineering majors, both mechanical and electrical. It's been ongoing now for about 13 years. So in the fall, we send a cohort of mechanical and electrical engineers for a full mechanical engineering juniors, electrical engineering seniors for a full semester abroad. And this program is carried out in partnership, an activity partnership with a school called Oniris. Oniris is in Nantes. It's within about a mile to a mile and a half walk from the main area that we rent houses from, that Growth City rents houses from to house our students. Oniris is a school that has basically two schools of learning. One is in the area of food science engineering. Yes, if you can believe it, food science engineering is actually a field of engineering. And then the other one is veterinary science. And we have a class in common that's taught with our GCC American students and Oniris French students in the same classroom. And they take classes that pretty much help kind of expose cultural differences and how to work through those differences. So it's one of the main attractions and one of our main activities for the class, in addition to courses that are simulcasted. So there's that program. It's currently run by Dr. and Mrs. Ruber. I am mostly carry out extra semester programs. This basically means travel courses. I team up with faculty to run travel courses, do the logistics, and then as well as started doing some summer research. And the summer research has been ongoing for about 6 or 7 years at this point. And I partnered up with our presenter, who I will introduce in a minute. We've been doing this research in the area of food process engineering, specifically food drying. And over the course of time, this research has grown to support the senior design, largely support senior design projects for the electrical engineering seniors that go abroad, as well as has developed a relationship of concurrent research between mechanical and electrical engineering department, along with the Department of Food Process Engineering at Oniris. This research has involved several mechanical electrical engineering professors on this side, several engineering professors on the Oniris side, as well as, I forget the count, but dozens of students in research and projects here. I have an ongoing research program here that students come on, as well as master's students and final year students at Oniris as well. So it's grown a lot, and it has largely been thanks to our speaker today. So our speaker today is Professor Michel Ave. He is a professor of food process engineering as well as deputy director of their research lab, and the acronym is JPI. I'm not going to go ahead and pronounce what it stands for, but it's their area of research, and they have a separate entity laboratory there that he's director of. So, and then largely also this whole event has been heavily sponsored by the Office of Global Programs. So we have a lot of people involved in this, and it's been a pleasure to see this happen. So I'm going to introduce Professor Habe.
Thank you, Professor Bardi, for inviting me, for providing me the opportunity to present this history of engineering research between Oniris and GCC. So you could continue because you speak very well English, I think. So sorry for my accent. I will try to speak as best as possible. So Eric said I'm working at Oniris, so I will first present you a short slide on Oniris and GPA. After, I will speak about two topics: EHD drying, the main program we work together, and the other program is the low-cost array data logger. I have a PhD degree in fluid mechanics and thermal engineering, but it's engineering, the field of engineering, and I'm working at Oniris in the Department of Food Process Engineering and more other, like said Eric. I'm a deputy director of a research unit called GPA. My field of expertise is food process engineering. I'm dealing with thermodynamics, heat and mass transfer, and it's applied for food process, thermal process, but also refrigeration, and I'm interested in energy efficiency. Oniris, when I saw this poster, I think it is important to say where is Oniris. In fact, you know where is France, probably. And Paris is here with Eiffel Tower, Notre Dame de Paris. Mont-Saint-Michel, also a well-known place. And Nantes is just 2 or 3 hours, 2 hours by car from Mont-Saint-Michel. So here are one of our buildings from the engineering site. Oniris is an allied graduate school specialized in food sciences and food processes, located in Nantes and in the aegis of the Ministry of Agriculture. We are about 40 lecturers. We have 400 students with different masters, food and nutrition, but also process engineering and health in collaboration with our colleague from veterinary school. We have several facilities, among them all of technology. I tried to convert a French unit to a British unit, so 2,000 square meter. With different, we can modify, change the place of equipment. And here you have students. It doesn't work. He's just looking at the apparatus. It's for experiments on EHD drying. In France, situation for research is a little bit different probably than in USA. So we are several institutions, Oniris, CMT Atlantic, and Nantes University, and the National French Council for Research. We work together on the field of process engineering for environment, energy, and also food. So we work together, and the actual staff is more than 200 researchers, and we are considered as one of the top research units in France for chemical engineering. Here it's chemical engineering, in France it's process engineering, so it's similar. So let's now go to the collaboration. In France, I work with other colleagues, professors. I involve also research engineers and technicians in our project, or in this collaboration, and some students, PhD students, master students. And from Grove City, I worked previously, firstly with Professor Eric Bardet, and also Marc Ruber, and not Marc Ruber. In French, it's Marc Ruber. And also Professor Mike Bright. Where is my? Yeah, very nice to see you. And several students. I don't remember exactly the number of students because they were from electrical engineering during the project in France. But also we have some discussion by a video conference, and so I met several students. And my field of interest is energy in food processes. It's why first. It was the main topic of collaboration with Professor Eric Bardet on what we call this EHD for electro-hydrodynamics, EHD drying. The collaboration starts 6 years ago with sabbatical semester 5 years ago of Professor Bardet in our laboratory. And since this period, he comes each year to perform experiments or to treat data with us. And he has the idea to involve some students from mechanical engineering and electrical engineering for their senior design project. And we continue with the collaboration with students on another topic, the low-cost array data logger. Eric was involved, like other colleagues from Grove City and students in this different project. So this is the two topics. I will speak first about drying. As you know, drying is a very common process. It allows to extend the shelf life of product, to store the products, to have out of season availability of these products. That is very famous process. But and in this process, mainly the dryers are convective dryers. We have to dry product using air. So we introduce air in the dryer, so it's just a sketch. It can be a batch dryer or a tunnel where the products are laid on several stages. The airflow is entering in the dryer, and then there is a heat and mass transfer. The objective is the dehydration. So we have to remove water by evaporation, and it's required a lot of energy because we have firstly to have air in very specific condition of temperature, humidity. Humidity should be low to allow the evaporation of the moisture from the product. We have also to blow air at high velocities because air is a quite poor heat transfer and mass transfer medium. So it results from a high energy consumption. In France, we have these figures. Closely to 20% of the energy consumed in the manufacturing industry is attributed to drying. Not only for food, there are several materials that require also drying. But it means that it's a very intensive process, energy intensive process. So our objective is to analyze the potential of a new process called the EHD drying. It's the context about drying. About EHD, I probably I look at Mike. Electrical engineers know very well this phenomena. When you have a ground electrode, it's the collector, we call the collector, and a very a pin electrode, for example, with a sharp radius of curvature. If you apply a high voltage to this electrode, you will generate what we call the ionic wind. So you have the current here, you have a ionization region where ions from the same polarity of the electrodes are produced and then go towards the ground electrode. Phenomena are rather complex, but the net effect is that it produces ionic wind or electric wind because ions collide with molecules in the air, and then you will see it can modify if we have an airflow, for example, an airflow coming from this side. With the ionic wind, we can alter the boundary layer flow and enhance heat or mass transfer. Eric, could you please? Here it's to show you it's a PIV experiment. In the channel, we have here a laser sheet, a camera, and by PIV technique, we can. Here you have the wire. I speak about a discharge electrode. It could be a pin electrode or a wire of small radius of curvature. With this wire, you can see that it completely modifies the airflow. You can show again, yes. We have some streamline first, horizontal, and when we apply the high voltage, it completely disturbs the flow, and it acts like a jet, air jet that modifies the airflow and may enhance its transfer. So with GCC, we perform experiments, several experiment investigation, in order to have information on the effect of this electric or ionic wind on heat transfer. So I speak about heat transfer because as mechanical engineers, there is analogy between heat and mass transfer. So it's easier to perform heat transfer measurements. We measure what we call the heat transfer coefficient at the surface of the ground electrode for several configurations. Several because we can modify the geometry. We can have several electrodes. We can have pin electrodes, wire electrodes. The gap between electrodes can vary. So several experiments can be performed, and they were performed. We can also play on the inlet air velocity and on the applied voltage. With this lot of data, we selected the best configuration for heat transfer enhancement, and we then conduct drying experiments on the best configurations. Moreover, we have data treatment to get information of the overall efficiency of this EHD drying process. I just show you some results quickly. For investigation the effect of ionic wind on heat transfer, in the channel we have the primary air velocity, the ground electrode, the wire, and at the top here we have a system that allows to measure the surface temperature here of the ground electrode by a specific device, and you have here the shadow of the wire, and it is the temperature of the plate, and it was first at this temperature in degrees Celsius. Did you give credit if they found in degree Fahrenheit? It's around 110 degrees Fahrenheit, and when you apply the high voltage, you reduce considerably the temperature. From this information, we are able to calculate the heat transfer coefficient, and we're in different situations. Here you have specific, we apply a voltage at the electrode, and we have to wait a threshold value before ionization starts. And when ionization starts, when you increase, you have this kind of curve, and you have to perform drying or heat transfer experiment in these conditions. So still an experiment, and when I have problem with one dot, doesn't matter. No, I have another curve previously here, but it was about the value of heat transfer enhancement due to ionic wind. So with Eric, we show that at low primary air velocity, we were able to have a great enhancement of heat transfer. We also perform EHD experiments. So EHD experiments for drying. It's the same channel with a specific air handling unit to provide air at desired temperature and moisture. We modify the system to have a balance, and we perform drying experiments. We perform drying experiments using not food sample, but a gel that have the same properties as the meat, thermal properties only. And we perform experiments of drying. This balance allows to have the weight losses evolving with time. So we recorded all the information with a data logger, and I could show several results, but I will focus just on this graph. You can see it is the time required for drying the gel. In conventional process, we blow air at 2 meters per second, and drying time is 15 hours. So it's classical process. If we use air at a lower velocity, only 0.3 meters per second, you will have very long, you can double the drying time. So it's not well operated at all. With the EHD technique, we are able to work at this air velocity, but as we add the ionic wind, it allows to increase the mass transfer, and we have shorter drying times. These drying times are in the same range of conventional drying times. We can improve by working on several other configurations of electrodes. But you can see that we are in the same range of dwelling times. And moreover, here, concerning energy efficiency, you can see that force convection, classical force convection, has a very low efficiency, whereas EHD techniques can increase a lot this energy efficiency. So there is a great interest of EHD drying because it has a high energy efficiency and it allows short drying times. Professor Luc Bardy will explain you probably what is the exergy efficiency. Mechanical for thermodynamics, we have this concept of exergy, and Professor Bardy developed a specific index for the exergy efficiency of the EHD drying process. I don't describe all the curve, but you can see that the exergy efficiency is very high for EHD compared to conventional product. It means that our system, based on EHD, better use the energy, the electrical energy provided in the system. At Oniris, we also perform other experiments on to dry real products like mushrooms, mangoes, prunes, and so I can say that it was a fruitful collaboration with GCC. Even Eric Bardy works with mangoes, but it was a real fruitful collaboration. We can discuss about this after. We demonstrate the great potential of EHD drying. We still need to improve the process, especially the scaling up for industry. And we would like to look at other convective food processes. And this morning I saw the system developed at GCC with help of funding of ASME. So it was a nice, it's a nice equipment. And we have some students working. It was very interesting for me to work with students on a project. This one was the first one that allows to develop the first apparatus at GCC. So you can see Paris, always Paris, and not Nantes for the photo. All the students coming in Nantes have the same photo. For me, it's a good transition for the second topic, low-cost array sensor, because I have the same photo. Not the same students, but same photo. So this team work on the low-cost array sensor. So I have also to introduce the topic. It's always on energy. As you know, in France we eat a lot of bread. Here also, not only bread, but we eat bread also, especially buns. And when you produce this bread, it requires a lot of energy. Imagine you have dough, a bread dough, with a lot of water, and you have to transform this dough to bread. So you have to remove water, you have to eat, you have to allow biochemical reactions. At Oniris, we have a great experience on the baking process. We have several ovens, like this one. It's deck ovens, but in industry there are long tunnels for baking process. You put the dough at the entry, and at the outlet you have the bread, but it can be 50-meter longs. And we have to control the quality of the bread. And to control the quality of the bread, we have to perform measurements. So these measurements are infrared measurements to control if the oven is well insulated or not. But what is important for us is to measure, to get information inside the oven, like this one, inside the oven. Or what is the temperature at different locations? What is the humidity? What is how heat is transferred by radiation and convection? So we have to perform measurement So when we perform measurements for temperature, it's quite easy. We have thermocouples, very easy to use. But for humidity, it's rather complex because, as I said, we have to work at very high temperature. Mainly, humidity sensor works at ambient temperature. When we work at very high temperature, we have to find new technology of sensors. This sensor have to measure during the baking time, half an hour, sometimes 50 minutes. As I said, it's mainly in continuous ovens, 50 meter long, and with a small gap entry, 10 centimeter, 4 inches. You have the door on the conveyor belt, and then a small gap entry to avoid heat coming from outside the oven, and then the bread go outside. And if we want to measure temperature, we need a sensor like this one. We need an electronic device with a battery because it should be autonomous, and an insulated box to protect against radiation and thermal effects the system. There is a system, this one, and the cost is around 40,000 euros, just this equipment. With this equipment, we have this kind of data. I don't discuss all the data, but we are able to have information on what happens during the baking time in the oven. We are also interested in getting information on heat fluxes. It is important for the quality of the product how heat is transferred to the product. Is this by radiation or by convection? We develop specific sensors like this one. It is a black system, black sensor, who allows the measurement of thermal convection and radiation. And this one is a gold plate that allows to measure only convection. Professor Baldi will explain you why it's only convection during this lecture. So this kind of system, this one is a commercial system. We have the sensor. We can so measure the heat fluxes. We have the electronic equipped part and the battery and the insulated box. This commercial system cost, it is very expensive, 30,000 euros. So with discussion with Rick Bardi, Mark Gruber, and we decided to look at challenging a new system. So it's with the information we can have with these ovens, we can perform some diagnostic how it operates. So the collaboration from this starting point, we decided to try to design a low-cost data logger to operate inside these tunnels, to record temperature from thermocouple, but also to record different signals for heat flux or for humidity, working during half an hour up to this temperature. So LCA features was low cost, a flexible programmability. It was a new experience for me because the students were working with Arduino. It should be easy to use, and so students have to work on these features. It allows a good experience because it was a mix between food engineers from Oniris and electrical and mechanical engineers from GCC, especially during their project. So one group performed a survey of the market. So you can see here for tunnel ovens, for more general purpose or for thermal validation. They found several equipments in commercial equipment, and they get information of the price of this equipment, or sometimes they estimated. And from this, they think that it was possible. They thought that it was possible to perform to a new system, the low-cost array. We can use it for all these markets and at this price. It was very, very challenging. But it was a very amazing experience. They built several systems like this one. They designed this. They also designed the box, and they perform experiments in ovens. And we, at the end, we have an equipment able to be used in the tunnels. So here are some students and my colleagues Luc who work with us on this project. Last year there were other students working for improving the system, and we have still to work, but from our laboratory we learn about this new way, instead of buying commercial system, trying to design them. So my talk is now finished. So I just want to show you that this collaboration allows to publish our results in scientific journal like Energy or Journal of Heat Transfer. It is a well-known journal in our community, our research community, and we also present our results in some conferences. Next, at the end of the month, one of my colleagues will be at Melbourne to present a review of our study research in this EHD drying. So I think the collaboration is also important and some students are going to, I don't remember, but the students, they went for a conference not so far from here. So it's interesting experience. And during one of these conferences, we received an award. Our paper was considered as the best paper award of the conference. So we were proud to receive this award, and it means that our work was very appreciated by the community. And so I would like to thank Professor Eric Bardy, Professor Mark Ruber, Mike Bright. So this professor were working with me during all this project. Thank you, Mike, for collaboration and your kindness. I would like also to thank previous engineers from GCC here at the name of for the electrical engineer during the project, but I met other students. And also special thanks to Professor Mark Graham for other reasons. You can imagine it's not for engineering. And thank you again for everybody for coming at these talks. And if you have any discussion, question, I can try to answer and to share the experience with students from GCC. It was a nice experience for me.